So a little bit about myself. I'm from Uruguay in South America. I study here first and work a little bit in exploration, mostly organic gold. Then I moved to Oregon. I was very lucky to study with John Diles, did my master's and my PhD there, and also got to work a lot with Scott Haley. So after that, I've been working as a consultant in mostly in porphyry space, either related with the geochemical side of things or the geological side of things in mapping and making cross sections and making observations on rocks. So today I'm going to be talking about the timing of hydrothermal alteration and veining and the relationship with copper and moly and gold mineralization in porphyry deposits, and trying to reconcile what we can see as exploration geologists. That's what I do, using a hand lens and doing core logging and mapping, and how we can reconcile those observations with microanalysis. So I have a long list of contributors there. I'm gonna mention a few, especially John Diles, Jaime Osorio, John Prophet, and Kalin Kuzmanov, who are co-authors in this paper that was published last year in Economic Geology. And also I need to thank First Quantum, who sponsored this research when it started during my PhD more than 10 years ago, and also through our consulting relationship. So the question I'm going to be focusing today is, when is copper introduced and precipitated in porphyries? And we can frame this question in two different hypotheses. So the first one comes from more the field side of things, and is the maybe more traditional one, and it comes from the observation of these typical porphyry veins called A veins that are very early in the paragenesis of porphyries, and they have a typical sugary or aplitic texture in the quartz. They have disseminated sulfide in the veins and also in the intermediate wall rock, and that's associated with hydrothermal K-feldspar and hydrothermal biotite. And if you look at a phase diagram like this one, that's an assemblage that we can infer relatively high temperature. So this kind of observation led to the idea that copper is introduced with these veins at high temperature in stability with K-silicate alteration. And if you need to put a round number to that, it has to happen about 450 degrees Celsius. And this comes to what Bertrand was discussing on how can you measure this temperature accurately. And it's not really important it's 450 or 470. It's just a round number to sort of think about the problem. More recently, when we start doing cathodoluminescence in quartz veins, and Bertrand showed several beautiful images of this. And if you have a look in cathodoluminescence of a quartz vein like this one, you see that in reality there are multiple generations of quartz in that vein. And this comes from early work from Patrick Redmond and Brian Rusk and Mike Reed. And if you see these sulfides that are disseminated within the A vein quartz, they are in many cases, or basically in every porphyry that has been seen with this technique, these sulfides in the A vein are in contact with a late generation of quartz that is dark in Cl or dull and cross-cuts the A vein quartz. And if you do different estimates of temperature in that quartz with fluid inclusions or titanium quartz, you get low temperatures. And to put a round number, below 450 degrees Celsius and as low as 300 or even lower. So this suggests that maybe the potassic alteration and the A veins were formed there first, and then the sulfides are introduced later with this later and lower temperature quartz. And that gained more traction with more recent work as studying these C veinlets or paint veins, which are not only cross-cutting A veins, but sometimes you can observe them on their own, and that also led to the idea that and they have this low temperature quartz, so that led to the idea that everything is introduced late and at low temperature. So to discuss this, we need to understand different vein types in porphyries. And I'm going to start by talking about two types of porphyries. There are many ways of differentiating families or subgroups of porphyries. We're going to talk about this in terms of depths of formation or emplacement. This is after work done by John Prophet. You can see this is a cartoon from Yerington. You have a precursor batholith, and one of the cupulas that it's shallower in the paleocrust has all these dikes and leads to the deposit known as the Yerington mine. That's what we know as a shallowly emplaced porphyry and called A vein type porphyry, because the ore, in despite of what's introduced in the copper, it's related in space with the occurrence of A veins. And this is a picture from Batu Hijau in Indonesia, which is also an A vein type porphyry, and you see the sugary texture, disseminated sulfide relationship with K silicate alteration, and they're biotite rich and magnetite rich. And from the same precursor batholith, you have another cupula, a bit deeper, and also deeper in the crust, another deposit called N Mason Pass, which is what we call a deep porphyry or an early halotype porphyry. And that's because the copper ore, is related in space with these alteration selvages called early halos rather than with A veins. There's not too many A veins in there. There's also K silicate or potassic alteration, but there's biotite with muscovite inside the halos, and magnetite is virtually absent. Could be a little bit, but not too much. And this is an example from Jaquira, Peru, what we call an EDM halo. So this is important because both type of porphyries are pretty common, right? A vein type porphyries are probably the best known ones. They have been better described in the literature. You see a lot of A veins are very abundant in the ore. They have truncation by different porphyry dikes, and early halos, now that more people are recognizing them, they are there, but they're not very abundant. And we mentioned Batu Hijau, Yerington, but also El Salvador, Chucarupeki in Serbia, or even Jebelo here, which is a pretty old deposit in Sudan. And we think all these deposits form at some point some depth that it's shallower than 5 kilometers. Then we have the early halotype deposits. Early halotypes, little bit of quartz veins. So it's the opposite. Early halos are abundant and A veins are rare, but they are present there too. So it's a continuum between these deposits. And we have Butte being one of the best examples, and Mason Pass, as we said, Jaquira in Peru, Los Pelambres in Chile, Pribrezhny in Kazakhstan, and even Haib, really old deposit in Namibia. And then we have some deposits that have characteristics of both, where there are some areas of the deposit where early halos are more abundant than A veins and vice versa. Bingham and Encuentro being that, and I think this class, it's gonna get a bit bigger with some time. So both type of porphyry deposits, they share characteristics in the timing of veining and the vein types that you have in there. So this is after Gustafsson and Hunt, the nomenclature of veinings. And the important thing here is the timing, right? It's what vein crosscut which vein. So we start with A veins. The Bertrand was showing many examples of all these veins. You have this sugary aplitic texture, and they are discontinuous, very irregular, sinuous, and you have disseminated sulfides. And then these are crosscut by B veins, which are more straight-walled. They have the oscillatory banding in CL imaging, and sometimes they have continuous center lines of copper sulfides too. Both of these stable with potassic alteration, and they have copper. At some point where potassic alteration ends, we start having those C veins or pain veins, where there's little quartz and there is some copper sulfide and some characteristics of going into chlorite and sericite alteration. And with sericitic alteration, it's well established. We have the very typical porphyry D veins, which have a straight pyrite center line and alteration selvages with abundant muscovite. Early halos, they fit in this picture at the same timing as A veins. Here's an example of an A vein cross-cutting and displacing an early halo, and sometimes we see the opposite relationship even in the same deposit, where you can observe both vein and halo types. And it's really difficult to know timing when it's a vein and a halo that cross-cut each other. early halos, they've been described for a really long time. Actually, before Gustafson and Hunt put that name and nomenclature on veins, these were described by Chuck Mayer for Butte. And there has been some confusion with D veins and the sericitic halos in D vein. And that's because these are the only two type of alteration selvages without a quartz vein inside. And we'll discuss this a little bit. There are many other names that have been used for early halos before, including EDMs, green mica halo, type 4 halos at Dos Pelambres. Even Gustafson and Hanna in El Salvador, they recognize this Andalusite corundum alteration. Sericita verde, very common name in South America. And we're also going to bring into the discussion of timing of veins, other vein generations of quartz, because not all the porphyry veins with quartz are A or B. We have deep quartz veins that are typically barren and predate A veins, more related to USTs and massive quartz. Banded molybdenite quartz veins that postate A veins and predate B veins, and they have moly but no copper. And some deposits have another moly generation with quartz after B veins. So we'll bring that into perspective in a minute. The other point that I wanted to make for this discussion is that not all the copper iron sulfide stringers within a porphyry are a C vein. They are only a C vein if you can see a cross-cutting relationship that tells you that they happen after A and B veins, or after early halos and B veins and BMQ veins and all these vein paragenesis. So it's very common to have examples like this one on the left, where you have a lightly colored early halo with, when you are in the higher copper grade zones, the dissemination of copper sulfides inside the halo, they start to amalgamate and they make these anastomosing sulfide stringers that are formed with the halo, and they evolve as the halo is growing. So sometimes they are slightly younger, but they predate B veins. So these are not C veins. This is one example, maybe a bit better of a C vein, but now I have some doubts too. This is an A vein, 2 generations of A veins and an early halo, and you see this sulfide-rich veinlet with very little quartz cross-cutting these veins. Okay? But we don't have the cross-cutting relationship with the B generation. And this is probably a C vein, but after doing some more detailed work here, the little bit of quartz that we have here, it's similar to the A vein. It's also sugary. It's just that there's very little bit of it, and there's hydrothermal biotite and gay feldspar in this vein. So it's very hard to know what's a real C vein without the cross-cutting relationships. I think this could be an A vein that is just very rich in sulfide and doesn't have much quartz. Coming back to the early halos, they look like this. EDMs, they're called early dark micaceous. It's the first type of halo that was described at Butte. Very probably easier to recognize and more difficult to confuse with younger D veins because they're dark, but they're not the only type of halos, right? And the mineralogy of these halos, it's K feldspar with muscovite and some biotite and some trace faces like andalusite that we're gonna see in a minute. So it's an alteration selvage along a central suture. There's not a central quartz vein. If it is, it's younger or older. And the fluid goes through the central suture and makes this alteration selvage around. And in this case, we're seeing that the halo, it's cross-cutting A veins, and it's obliquely reopened by a B vein. There are early halos that are much lighter in color, and they're actually, I think, more abundant than EDMs. And to put some order in all these nomenclature, we call them pale green sericite or green gray sericite. It's been names that have been used before. They share the same characteristics of all early halos. They have K feldspar muscovite biotite. They are irregular in shape. They have these anastomosing sulfide center lines. And it's just that they have a little bit less of biotite or traces of biotite, and it really tricks your eye into looking at color. Okay, but the key thing here is that they are early. They're equally early to EDM halos. So we name all of these early halos rather than giving specific names. even the ones that are very light in color and they have abundant muscovite and almost no biotite or traces of biotite, they have andalusite as a trace. And it's something that now that we have access to tools like this, it's a ChemScan or a TIMA image where you can see in very much detail the mineralogy of alteration. We're starting to see this more clearly. So this is also an assemblage that it's a pretty high temperature. And in this case, we use this same green-gray sericite for these lightly colored halos. And the ones that look more gray, they just have no biotite or just traces of biotite. The ones that look more green in this very light color version of halos, they have just a little bit more of biotite. And that's what gives the greenish color. It's not the abundance of chloride or smectite. But it's common to have intermediate GD overprints in all these halos. And that doesn't really change too much the color unless it's very intense. Very common to have hydrothermal biotite partially replaced by vermiculite, which gives hydrobiotite. So color is not a very good guide. The important thing is the timing and the mineralogy. So to put them all together, we can see from left to right, darker to intermediate colors to very light colors, and these subtypes of EDMs, PGS, and GGS. They all share the same mineralogy, as I was saying, feldspar muscovite, which is phengitic, with some biotite, and they have a shreddy texture, as we see in the wall rock too. And they're contained within a potassic or K-silicate alteration with more shreddy biotite. And what changes is the amount of biotite. So the lighter color, the less biotite they have. This is how it looks on a ChemScan. And if you see, this is K-feldspar. The green is biotite, muscovite in this reddish color, and chalcopyrite. And when you go from EDM to pale green sericite, there's less biotite, and when you get to green-gray sericite, there are just traces of biotite. But the other mineralogy is still the same. The abundance of the biotite is related to the iron content of the wall rock. So the early halotype porphyries emplaced in more mafic to intermediate wall rock, like Hakira and Butte, that they are in granodiorites, you tend to see more EDMs or pale green sericite type of halos because there's more iron and you favor the formation of biotite rather than muscovite. When you get to very felsic systems like Tacataca in Argentina, that it's hosted in a slightly, well, not slightly, in an older granite, there's not much iron in there. There's not much mafic content, and you only produce these very light color halos. And that's also related to the copper grade that you can host in the halos. So these they struggle to go above 0.3 copper because there's not much iron to precipitate the sulfides, and these could have much higher grade. Nonetheless, the light color ones could make big and nice deposits too. The other controlling the mineralogy of the halos is the fluid to rock ratio, and that's why it's better to name them all early halos than to use these subtypes, because it's very common to have zonation in the halo. So the center area here, where you have these sulfide center lines, has more muscovite and biotite because there's more fluid going through here, and there's more acidic conditions over time. The rock loses the buffering capacity, and as you go to the edges, you preserve more, you form more hydrothermal biotite, and you preserve more biotite of the wall rock. So that's also very common. So bringing all that together, I talked about differences between the early halo porphyries and the A-vein porphyries, and there are many similarities. One of them is that the ore zone in both types is contained within the K-silicate alter zone, where there are porphyry dikes, and the copper ore zone is related to chutes where you have high density of A-veins or early halos, or both, and they're both contained in the potassic zone. And then the other point that I mentioned before is that not all the quartz veins in a porphyry deposit are A or B veins. We have other generations of veins. Here are some examples of what we call banded molybdenite quartz veins, or BMQ. These were described very early on without that name. This is work by Nielsen in the 80s from the Santa Rita stock. where you can see that banding. And the characteristic thing they have is that you don't have the sugary texture that you have in A veins. You don't have the oscillatory banding and open space that you have in B veins. These occur in between A and B. You have more massive quartz, and you have molybdenite, especially in the edges in bands and some in the center, and no copper sulfides. Okay, and these are common mostly common in early halotype deposits because those are moly rich, but they're present in all porphyries. Even this is from climax, so you have these are called railroad track moly or something like that, and it's the same morphology and at a very similar timing with alteration halos in those deposits too. So I will say that these moly porphyries are also of the early halotype family. Especially in South America, these were recognized as B veins before because they are commonly reopened by B veins. When you see this in cathodoluminescence, you see that the texture in the center line is different, and that's where you have the copper sulfides. So this is a reopening of a banded molybdenite quartz by a B vein. And actually, this was described by Gustafson and Hunt, where they recognize that deeper parts of the deposit have that, and that could be an independent vein generation. So it's important for the discussion because they have molybdenite, and when they're not reopened, they don't have copper. Then we have older veins that they predate A veins, and we call them deep quartz veins. They were previously named barren quartz vein at Butte, barren Stockwell veins at Bingham, barren A veins at Batu Hijau. We kind of avoid that name now because they don't have the sugary texture of A veins. They are not sinuous, they're not intermittent, they're more massive, milky, coarse grain. The inclusions of other minerals inside, like magnetite in this case, is also coarse grain, and they're closer in time to USTs and massive quartz and apletic dikes. So in this case, they're uplights that are cross-cut by deep quartz veins and uplights that cross-cut the quartz veins, which leads to these what we call vein dikes, which is deep quartz vein reopening uplights and uplights reopening deep quartz veins. So these are also important in the discussion because they don't have sulfides. And they are cross-cut by A veins and B veins and BMQ veins. So we can go back to the question of when copper is introduced and precipitated. And now in these two hypothesis frame, we can introduce this diversity. And it's important because, for example, in the early halos, we have a different perspective at this issue of the quartz timing because we don't have much quartz. And we see the sulfides in contact with other silicates that give us temperature information. And then in the ore zones in these deposits where you have the high-grade copper, you have barren quartz veins and veins with moly that don't have copper sulfides, and they're also affected by these multiple generations. So this is what we discussed in that paper published last year. We looked at 3 deposits, the Pórfido deposit that capture this diversity from early halotypes to A veins. So we have Jaquira, Peru, in the Andahuaylas belt, probably form 8 to 10 kilometer depth. Typical early halotype, very similar to Butte. Batu Hijau in Indonesia, probably form around 2 kilometer depth. And something in between, which have both type of veins and shared characteristics of both types, which is Encuentro in the Centinela district of Chile. And the good thing of these 3 deposits is that they're relatively simple in terms of repetition of events and overprints. So they have a more simple progression of veins through time without too many overprints of different vein types and different alteration. And what we see in these deposits that they have been extensively logged from the perspective of looking at vein types, cross-cutting relationships, and the distribution of these veins in space is that there is an intimate relationship between potassic alteration, the abundance of quartz A veins in particular, or early halos, or both, and the copper ore. And the veins that are unambiguously C veins, they are volumetrically minor in the systems. So from this pure field point of view, there is a very strong correlation with these early veins, either A veins or early halos, and potassic alteration and the ore. And this has been described for deposits where this type of work has been done. And as I said before, all these deposits, they share characteristics. These three deposits have the key vein types and halos. They are observed in all three deposits, and the timing is virtually the same. So if we put together all the veining in these deposits in this schematic cartoon, it looks like that. That's wall rock. There's a porphyry dike, has a quartz phenocryst there. And then the first event, it's what we call this deep quartz vein, which are barren. They don't have sulfides. This is crosscut by A veins, sugary, plitic, discontinuous, irregular. Some are very sulfide rich, some are not. And early halos or early halos, also with disseminated sulfides, sometimes having a lot of anastomosing sulfides inside the halos. Then these are crosscut by the BMQ veins, which have molybdenite in these bands, but they don't have copper sulfides, and they crosscut in space in the same areas of the deposit, right? And then these are in turn crosscut by B veins, which have mostly copper sulfide, but they could have some moly in there too. And when we apply cathodoluminescence to these and try to see textures, and there's also quartz moly veins that crosscut B veins in some deposits like Encuentro or El Teniente, for example. And all these veins that I mentioned until now, when we look at in cathodoluminescence, they have lucent Cl quartz. So all the variations of the brighter Cl types, and they're all stable with potassic alteration. The veins that follow, which are C veins with little quartz, but when you see quartz, it's not lucent anymore. It's what we call dull Cl quartz or dark Cl quartz. We see some indications of C veins being part of the central lines of some B veins. And then we have D veins, where there's absolutely no more lucent quartz at all. It's all dual Cl quartz types with abundant pyrite and muscovite, and only copper sulfides, where these veins crosscut older veins that have copper sulfides. So there's a big change from all the older veins from 1 to 6 here when you get into the C and D veins. And then when you look in detail in cathodoluminescence inside all the older lucent Cl quartz, we see that these microfractures with dual Cl quartz are everywhere. They crosscut all the vein types. They're not only present in A veins, they are present in all these veins. So we think that each of these veins on the earlier lucent Cl quartz generations are formed with their own distinct population of sulfides. Some have copper sulfides, some are barren, some have only molybdenite and don't have copper sulfides. And then the dull Cl quartz that is late and much lower temperature percolates through microfractures that affect all these lucent Cl quartz, and they become in contact with whatever minerals are included inside those vein generations. So no sulfides in deep quartz veins. It becomes in contact with copper sulfides in A veins with moly and banded molybdenite quartz. So I'm going to show you some examples of what we've seen at this microanalysis scale. So this is a ChemScan image from an early halo. You see these are the feldspar, magmatic feldspar in the wall rock, and when you're inside the halo, they look like that. So they're completely replaced. And you can see a summary here of that replacement. It's K feldspar, phengite, and biotite. And we discussed before that there's some andalusite in there too, and other phases. And what we see in terms of the sulfides is that chalcopyrite and bornite are usually completely enclosed in K feldspar or in between shreddy muscovite, biotite, and K feldspar, which shows that these sulfides are precipitated with these silicates during the formation of the early halos, and it has to happen at relatively high temperature, above that 450 degree. When we go to the A veins, we see this observation that has been seen and documented very well in every porphyry that has been studied with cathodoluminescence. That is that there's a lot of contact of copper sulfide in A veins with the darker dull Cl quartz that it's younger. In some cases, the sulfides are completely included in these late quartz. But we also see that there are some sulfides that are mostly included or completely included in the older lucent quartz, which is the pink sugary texture quartz here. We see terminations of the younger quartz against the sulfide and stuff like that. And more interesting, we see that other minerals that are inside the A veins, like anhydrite and K feldspar, they also come in contact, are in contact with the dark Cl quartz. And in some cases, the dark Cl quartz completely surround this mineral. So we think that's evidence of sulfides, anhydrite, K feldspar, they were all here. And then the dark Cl quartz precipitated along those fractures. And this is maybe better explained if we see this in the context of cross-cutting relationships. So this schematic drawing is showing a deep quartz vein, a quartz phenocryst in a porphyry that is cross-cut by an A vein with copper sulfides and an early halo with sulfides. And there are no sulfides in the deep quartz veins and the quartz phenocryst. However, when you see it in catoluminescence, it's all almost equally cross-cut by this late dark Cl quartz. So the only way to explain this cross-cutting relationship, because these occur in the same piece of core, in the same intercept, is that these sulfides were in the A veins and the early halos that cross-cut these veins that are barren, and then these late dark Cl quartz come later. This is also reinforced if you see a younger time slot in the evolution of the system, where you have A veins and early halos here that are cross-cut by banded molybdenite quartz veins that only have moly, and that one is cross-cut by a B vein with moly and copper sulfides. And when you look at the catoluminescence, you see the sulfides in contact with no quartz in the early halos, biotite, K feldspar, muscovite, in contact with dark Cl and bright Cl quartz in the A veins. And then you see the dark Cl quartz in contact with molybdenite only in these banded molybdenite quartz veins, and both in contact with copper and moly in the B veins that are cross-cutting in the same space. So again, this is explained by having the sulfides as part of these veins before the dark Cl quartz was introduced. And when you look at C veins and D veins, as Bertrand was showing nice pictures of these, you get into these very dark Cl and low titanium types of quartz. There's a lot of muscovite inclusions. And when you see cross-cutting relationships of a D vein cross-cutting an A vein, you see dark Cl quartz or dull Cl quartz cross-cutting lucent Cl quartz. So you see the same type of quartz and the same cross-cutting relationship that you see in the microfractures through all other A veins. So we think this suggests that this dull Cl quartz in microfractures, it's introduced close in time with the formation of C veins and D veins and the onset of sericitic alteration. So reconciling these two hypotheses in base of these observations, we propose that the bulk of the copper is introduced and precipitated with early halos or A veins, together with this lucent Cl quartz and instability with K-city gate alteration. And similarly, the bulk of moly, if there's enough moly there, it's introduced and precipitated in later events with banded molybdenite quartz veins or MQ veins. And then there's some more of both of those with B and C veins. And at the later stage, when the system it's dying, it's the first time when you go from potassic alteration to sericitic alteration that the system is going to sustain a prolonged cooling and it's not going to heat up anymore. And at that point is where everything cools down, and the high temperature quartz, as it cools down, it's going to contract. So there's a volume reduction on all the lucent Cl quartz generations. They're going to fracture to accommodate that volume reduction. And also that volume reduction overlaps in temperature with the field of retrograde solubility of quartz at low pressure. So any fluid migrating to these fractures that are produced by volume reduction will produce some dissolution and erosion, okay, further enhancing the permeability of these fractures. And we think that's why it's so common to observe in A veins, in particular, copper sulfides in contact with the dark Cl quartz. It's because the copper sulfides and quartz are crystals together, are grain boundaries discontinuities that are pre-existent before the volume reduction. So when the lucent quartz cools down, some of this volume reduction is gonna be accommodated in those interfaces between crystals. So it's gonna be open space for that microfracture to expand and the fluid to precipitate there. And the same for the observation of dark sealed quartz with a hydride or K-feldspar or anything in those veins. So then what's different between early halo type porphyries and A-vein type porphyries? Because the temperature of precipitation of the copper and the timing seems to be very similar, right? What we think is different is the pressure, and that's what ties back to the depth of formation. So this diagram is pressure against temperature, and you see these gray lines are the solubility of quartz. So what you see here is that if you start with a fluid at relatively low pressure, so an A-vein type porphyry like Yerington or Batu-Hijau, when you release fluid from the cupula and it starts to cool down and upflow, it's gonna release pressure and cool down and precipitate copper, right? Because precipitate quartz, because it's gonna be cross-cutting these solubility fields of quartz. And when you arrive to that window of 450 to 550, when A veins and B veins are formed, you are still prograding and precipitating quartz. In the case of deep porphyries like Hakira or Butte, that fluid release at higher pressure is going to have a similar trajectory and precipitate quartz early on, probably where you produce these deep quartz veins in the center of the systems. But when you arrive to that window, 550, 450, you are in retrograde solubility of quartz. That more than real retrograde, I think it's just a bit of inhibition of quartz precipitation. And that favors the formation of the alteration halos and not precipitating veins. The other part of the story here is probably that the formation of acid from SO2 is pressure dependent. So in the high pressure systems, you produce more acid early on, and that's probably why you have muscovite with the early halos together with biotite and K-feldspar, and why there's no magnetite in these deep systems. So after talking for more than 40 minutes on timing and temperature, I'm gonna put my exploration hat and think about how important it is to know the exact temperature of precipitation of copper for exploration. This relates to what Bertrand was saying of knowing the exact temperatures. And I think the answer is that it's not that important at all. But I think that the questions we need to ask to try to answer this are really important, and trying to answer those are really important. And that's understanding veining and alteration types and the timing and evolution of that in porphyries. And this is from a recent paper from Dick Silito and Pepe Perechot, and it highlights that mapping it's still really important in core lowing, and mapping potassic alteration and quartz vein types. It's an essential exploration tool. So most of the high-grade copper in porphyries is associated with potassic alteration, and if it's not, it's in many cases it's because the potassic is masked by overprinting events. And the high density of quartz veins, it's also related to high-grade copper, right? And those quartz veins are in vast majority A veins. We can add to this story a little bit of complexity in terms of the deep quartz veins and B veins and that, and I'm going to expand a little bit on that. And that's why we need to have a nomenclature of the veins, that it's based not only mineralogy, but in cross-cutting relationships, because we need to have time to compare different generations. All these vein types, they are not, they have their own variation. So we need to have this timing to name a certain mineralogical group of variability. And that lets us compare across prospects, see what's similar and what's different between small porphyries and barren porphyries and economic porphyries and gigantic porphyries. And I think in some cases, if you're early on in exploration and you have copper hits, but they're not associated to the right type of vein, being A veins or early halos, there are chances you have a sub-economic porphyry more than an economic porphyry. This also takes some time and some effort. It's not easy if you are in an exploration project and your first meter of core gives you that. You will struggle to know if that's an early halo or a sericitic halo to a D vein, or grace and alteration even, or intermediate Gower prints. And that's because we need to have those cross-cutting relationships. So this is something that needs to evolve as you do the exploration. And now we have access to these mineralogical tools like ChemScan and traditional petrography too. We need to make an effort to understand that mineralogy. So I'm gonna wrap up with a couple of slides on some thoughts for exploration too. I think one that it's related to everything that we've been discussing is that shallow and deep porphyries are explored differently, and A-vein type porphyries are economic in copper and gold. They have little moly, and they have some characteristics besides having A-veins, is that they're hosted in the highest grade hosted in the oldest porphyries, and the mineralization is truncated against contacts with younger porphyries. So the effort of trying to find the early porphyry, it's really important and crucial. They're also magnetite and biotite rich, so geophysics, magnetics are going to behave in one way. Early halo type porphyries are pretty different. They are copper moly rich and they have little gold. If gold is associated, its present is associated with bornite in the top of the barren core, so sort of in the center of the deposit of the inverted cup shape zone. The mineralization is hosted usually in the wall rock, which could be the precursor batholith or a related stock or older volcanic or magmatic sedimentary rock. Brechas and high-grade copper brechas are common in these deposits too. And the porphyries that are closest in age to the formation of the deposit are very thin dikes and deep in the system. So there are not many truncations of mineralization by porphyry dikes. And there's not too much sense in finding the early porphyry in exploring an early halotype porphyry. They're also magnetite poor, and there's muscovite in the center of the deposit. So the geophysics, the magnetics of an early halotype porphyry is going to be the opposite of an A-vein type. And then in terms of vein density, in A-vein type porphyries, the highest quartz vein density is coincident with the ore zone because of the A-veins, and it continues into the deep quartz vein zone in the barren core. Sometimes that zonation is disrupted because you have younger porphyries that are barren and veinless in the barren core. So in those cases, you end up, if you map quartz vein distribution, the most amount of quartz veins are in the ore. In the early halotype porphyries, the highest quartz vein density, it's coincident with the barren core below the ore, because the ore is associated with early halos on top of that barren core, and there's not much quartz vein. So this is an example from Hakira, comparing Hakira with Batu Hijau. That's sort of half of a shell of the copper shell in Hakira, 0.5 copper, early halos, A and B veins. There's a barren core here, and the highest density of these deep quartz veins are down there in the barren core. So if you have a prospect that it's outcropping at that depth and it's full of quartz veins, could be that it's too deep and there's not much copper in there. Whereas if it's an A vein type like Batu Hijau, there is a high abundance of A veins to deep quartz veins throughout the deposit and its roots, and you have that disruption by younger porphyries. And two more points in there is that muscovite is not a synonym of sericitic alteration anymore. We have muscovite in sericitic alteration associated with D veins, especially in the tops of the porphyries and periphery, or in D veins that cross-cut and are overimposed the K silicate zone. But we have abundant, especially fengite in early halos, in the K silicate zone. This was very early described by Cini in the inside-out porphyry model in the 70s. So there's muscovite in there too, and we also have Grayson alteration that not every porphyry has it. It postdates the porphyry. It's related to the precursor batholith below, but you could have abundant muscovite even if the porphyry is eroded in the roots. Similar situation now with albite. Albite is not only forming sodic alteration, like this example here, we see some relict magmatic anorthite, some K feldspar, and there's a wash of albite in this blue color that it's overprinting everything. And when you look at the whole rock, the whole rock, it's gaining sodium. But now that we have ChemScan, we're seeing albite in many places. This is our A veins with K feldspar halos in orange, and related to those A veins and K silicate alteration, where even the rock it's gaining potassium and losing sodium, we see albite. And this has been kind of misleading in interpretations. This albite, it's not added sodium, it's just during K silicate alteration when the albite portion of anorthite recrystallize to K feldspar to accommodate the added potassium. There is no more fit for sodium that was hosted in the anorthite, and some portions of that anorthite need to recrystallize into albite. So we need to be careful with that. So that's all. Thank you.
All right, thank you so much, Federico.